I would like to give you an overview on typical partial discharge sources in large rotating machines. The insulation systems we use today for rotating machines are inherently resistant against partial discharges because of their inorganic mica components. The insulation system is subjected to several stresses during operation. The main stresses are thermal stresses, mechanical stresses, electrical stresses, and some factors from the ambient that all contribute to insulation aging. Even if the material itself is very resistant against partial discharges, these discharges can efficiently be used to detect insulation aging due to these stress factors. And typical sources of PD are void discharges, voids within the main insulation that can usually not be avoided during the manufacturing process. These discharges are more critical for the insulation since they may attack the strand insulation or the turn insulation of the conductor. And in addition, the thermal conductivity is decreased by these delaminations, maybe leading to a thermal runaway. In addition, we may have some slot discharges between the main insulation and the stator core, which are really critical for the insulation. And then we have some typical discharge sources within the end winding area of the machine. There may be discharges in the slot exit region due to vibrations, damage due to vibrations. There may be discharges within the field grading area at the end corona protection if this end corona protection becomes ineffective due to porosity, contamination, or something else. And there may be discharges within several locations of the overhang part of the machine, in the face separations or somewhere else in the overhang support system, like at spacers or something. Okay. We can measure these partial discharges and use these discharges very efficiently for getting information about the stator winding insulation condition. The measurement itself can be performed in two different ways. We usually have offline testing for partial discharge measurement and online testing. And there are several advantages and disadvantages for these measurements. One main difference is that for offline testing, we need an external power supply, an external test transformer, because the motor is from the grid. And for online testing, we use the normal face-to-ground voltage as a testing voltage. The signals, the PD signals within the stator winding are detected with capacitive couplers, and these signals are then fed to an amplifier and filter hardware with special characteristics. And after that, the data can be pre-processed with the computer and analyzed with some kinds of expert system. Today, the main type of expert system is the human expert for assessing the partial discharge data. These data are analyzed with some pattern recognition methods, and after that, a diagnostic decision is derived. What is very important for PD data analysis is to perform a trend analysis with the data, because this gives the most important information. It means that to perform one individual measurement on one particular machine gives not very much information about the condition of the stator winding, because we don't know how the discharge behavior develops. So we need a trend analysis of the data for a reliable condition-based maintenance. There are several advantages and disadvantages for online and offline PD measurements. The most important advantages for online measurements are that there are realistic stress conditions within the stator winding insulation. We have realistic electric field distributions, currents, mechanical forces, vibrations, and temperature conditions within the machine. There is no interruption needed, so the method is very cost effective. We can perform easy trending over time. We can perform an early detection of impending insulation faults with this method. And we need no external power supply for energizing the winding. There are, however, some disadvantages for online measurements, and the most important ones are that there's considerable interference and noise during the measurement. Noise may mask actual problems of the machine. There is a strong superposition of several PD sources, and a localization of PD sources is more difficult than with offline methods. For offline methods, we have also some advantages and disadvantages. We have a lower interference level. We have voltage variability, so we can measure the PD inception and PD extinction voltage. And we can apply additional dielectric measurements, for example, visual inspection, and we can perform some maintenance work if needed. The disadvantages are that we have to supply an external power source. The machine must be out of service. It's very time consuming and therefore expensive. And the entire winding, inclusive the neutral end of the winding, is at high potential. So we have no realistic stress conditions. Okay, what is all this intended for? The main aim is to get a reliable condition assessment of the stator winding insulation. We will use this condition assessment for preventive maintenance planning. We will use it for optimizing our reinvestment planning. We will optimize our schedules for normal machine outages, for offline diagnosis, and we can reduce the in-service failure rates by applying these methods. And the main aim is to maximize the reliability and availability of the equipment. There are, however, some intrinsic limitations for partial discharge measurement on rotating machines. And the first one is that we have no PD specifications for rotating machines where limits are defined for good or bad machines for acceptance tests during manufacturing or during operation. And this is, however, impossible to define because it depends too much on several parameters. It depends on the condition of the measurement and on the machine itself. We have strong pulse propagation phenomena within this highly inductive winding. The machine itself acts like a filter with special filter characteristics, and this means that we have PD sources within the winding and couplers on the face leads, and we don't really know the transfer function between the PD source and the coupler. So it means that depending on the machine characteristics, depending on this filter characteristics, we will get different readings for the measurement. We have strong overlap of simultaneous PD phenomena within the winding. The correlation to other dielectric tests is not yet clear. The comparison of results is only valid under special conditions. It is valid for the same machine under similar conditions using the same equipment, and the results will very much depend on the test method we use and on the conditions during the measurement. And especially what is most important, it will depend very much on the machine design. So we need a lot of knowledge about the machine design features, about insulation material characteristics, and about the interaction of several physical and chemical processes within these insulation systems. Now I want to show you some examples for typical discharges resulting from high voltage machines. Here we see some examples measured on turbo generators during operation. It's an online measurement. You see here some slot discharges at half load that may disappear at full load because of different temperature and current conditions within the winding. This is just an example that may look quite different for other conditions or other machine designs. The next example shows you typical discharge patterns from internal discharges within the main insulation, discharges from voids. You see two examples for turbo generators with void discharges, and these discharges are usually very uncritical for the machine because the insulation system itself is inherently resistant against these inner discharges. The next example shows you some typical patterns resulting from end winding discharges, also measured on turbo generators in operation. The first one shows some discharges in the region of the end corona protection, and this type of insulation deficiency is quite easily fixed by reapplying some semiconductive varnish within the end winding area, and after that you usually will not find this pattern anymore. The second example shows you an online measurement on a turbo generator that is operated in a steel production site, and during this measurement a pattern was found that indicated that there are floating metallic particles within the end winding area. After that diagnostic decision, the machine was shut down within a few hours, then visual inspection was performed, and indeed there was highly conductive dust found within the end winding area. The machine was carefully cleaned, put into operation again, and then these critical discharges were no longer found. This shows you a typical example for a combination of inner discharges from voids and slot exit discharges measured on a hydro generator. Now we have seen a lot of discharge patterns, and I will show you now typical sources within machines where you can find the discharges leading to these patterns. This shows you an example for slot discharges. You see here these indications for the discharges. On the right side, there is an example for slot exit discharges. And here we can see discharge sources within the phase separations and discharges in the overhang support system of the end winding. The next example shows you typical discharge sources within the slot exit region of a hydro generator due to some damage because of vibrations of the bars. Here we have an example for discharges in the area of the phase separation of the machine. All these examples showed some typical PD patterns that could be very well correlated with typical PD sources within the machine. And what we want to prevent with this kind of measurement and analysis is something like this, which shows you an in-service failure, an insulation breakdown during operation of the machine. And in this case, there were no measurements carried out, no partial discharge measurements carried out prior to the breakdown of the insulation. However, there may be also conditions in the insulation system where PD measurements are not able to indicate an impending insulation fault, as I will show now. Here you see an example for a measurement on a turbo generator, which was monitored by PD online measurements in regular intervals. A test was carried out in '97 where no critical PD behavior was found, only low-level inner discharges. So there was no critical situation for the insulation system. The next measurement was carried out in June '98. Again, no critical PD behavior was found, only low-level inner discharges and very slight indications of some PD within the end winding area. But these PD were within the expected range for this kind of insulation system and for this type of machine. So there was no indication of critical PD. The only indication that there was something, there seemed to be something wrong with the machine was that one of the RTDs showed a temperature that was about 25% higher than the other ones. And this showed that there was a process going on in the machine with some local overheating. Before the actual cause for this local overheating could be determined, the machine itself changed its appearance very much, and shortly after the second online PD measurement, it looked like this. An insulation breakdown occurred without any pre-indication by PD. The examination of this insulation fault showed that there was a kind of interturn insulation failure with circulating currents within the winding that led to a local overheating and finally led to a thermal runaway and therefore to insulation breakdown. This type of insulation defect could not be detected by PD measurements since there were no pulse-shaped local electrical discharges. Instead, this breakdown of the stator winding was associated with continuous leakage currents within the winding, leading to local overheating without any locally high electric field, which is required for partial discharge inception. Therefore, this failure could not be detected. Okay, to assess PD diagnosis on rotating machines, I can summarize that PD measurement is a powerful tool for reliable detection of locally confined insulation defects, for condition-based machine diagnosis, especially when applying online methods, and a powerful tool for optimized planning of preventive maintenance. However, PD diagnosis requires a profound experience in the assessment of PD results. It requires a large database for comparative analysis, a large knowledge on machine design parameters, and it requires a trend analysis, a trend investigation of these PD data. PD diagnosis is not a tool that allows to discover all insulation problems within stator winding insulations, e.g. pulseless discharge phenomena, or all phenomena associated with low voltage but high currents can in principle not be detected by PD measurements. So PD diagnosis needs to be combined with other diagnostic tools like visual inspection or other dielectric tests, and it needs to be integrated into a general diagnostic concept. Finally, I will show you some future trends in PD diagnosis on large rotating machines and a concept for stator winding insulation diagnosis. One point is the worldwide remote access to online PD measurements in power plants to optimize the strategies for condition-based maintenance of the machines. We will try to improve our data analysis and assessment of the results by the application of new PD parameters for the PD analysis. for example, by introducing delta U parameters derived from the pulse sequence analysis. We will introduce modern pattern recognition algorithms for computer-aided machine diagnosis by expert systems. And first experience at ABB has clearly shown that using these tools, a significant improvement can be obtained in this area. Finally, I will show you our concept for state winding insulation diagnosis as performed today. We have a diagnostic inspection of the machine using several tools like the ABB VideoPro or the ABB PAMOS system. We use a huge diagnostic database that contains a lot of inspections on several machines diagnosed by various methods. It contains information on the operation condition of the machine and on maintenance actions from the past. This diagnostic database contains over 2,000 machines from different manufacturers, so we have the chance to make a lot of comparisons when analyzing the results. In addition, we use a so-called expert system for making the diagnosis. This expert system consists of well-experienced diagnostic engineers that have a lot of knowledge on the insulation systems and especially on the machine design. And there is, to support these diagnostic engineers in their decision, we have a computer system using some modern algorithms like neural network or fuzzy algorithms for making the data analysis and especially for trend analysis to arrive at a condition assessment of the state of winding insulation. This finally leads to the diagnostic decision concerning the state of winding insulation system and in some cases to preventive maintenance work that should be done on the machine.